Okay, so here is everything that's left this semester. The makeup exams are a week from today. So Thursday, 5/8. You could also take it with the night class, Wednesday, 5/7. And that's not the same exam. It's the same topic, but different questions. Yep. How am I going to know? I'll just bring in a stack of all of them, each of them. And there'll be a quiz on there, but if you're happy with your first quiz grade, say, you can skip the quiz. Like I'll keep the higher score of each of the two, you know what I mean? So if you had a good quiz score on exam 3 and you're retaking exam 3, you can just skip the quiz, go right to the test, and I'll just keep your old quiz score. And then hopefully, if you improve your exam score, then I'll take the better exam score. Okay, and then the final, exam 5, is during our scheduled final period, and I don't remember what time that is, but I'll get that up on D2L, but I know it's on Tuesday. So Tuesday, 5/13. It is at 11? Thanks. And the topics on this are going to be electromagnetic induction. That's what we're talking about today and Tuesday. And then it's also cumulative. So you need to go back and remind yourself about all those old practice problems. And that'll be written to be like the same length as our other exams, but you have 3 hours to work on it, so time definitely won't be an issue on this one. But so, you have 3 hours to work on it, but it's not going to take anyone 3 hours, I don't think. Well, that's not really true. Usually there's 1 or 2 people who stay the whole time, I think, trying to like derive the laws of physics from thin air, or whatever, But yeah, so to get ready for it, just go over the practice problems. The exam is going to be the same format. I'm going to, so there'll probably be 6 total questions. 2 will be on electromagnetic induction. The other 4 will be on old stuff. And the 4 ones from the older stuff will probably be a little bit simpler, a little bit. I mean, sort of in the same ballpark as the other exams, but they'll be a little simpler and a little shorter so that I can fit in a couple more questions in the same amount of time. I think you're thinking of a different class.
I remember I asked you last time.
Okay, I'll check the video. So that's exam 5. Any questions about either of the tests? And then problem set 2. Is due, you have to turn this in by the end of finals week. And that is Friday, 516. And there are two questions on here. The first one is make up a single problem with each of these three things in it. An electric field calculation, a circuit, like solving a circuit, and a calculation with electricity and magnetism. So you have to fit those in, but other than that, you have complete freedom, make up your own numbers. But it has to make sense with all the rules that we've talked about with these things, you know. And then the second question is write an outline of the topics covered in this class. If you handwrite this, this should be about a page long. If you type it, it should be more like half a page long, so not a very long thing. I just want you to go through your notes, remind yourself what all the topics were, what the order was, what topics were, you know, inside. So an example here would be like, okay, so number one, we talked about vibrations or harmonic motion, whatever you want to call it. And we talked about spring mass systems, pendulums, then we talked about waves. What did we talk about in waves? Just how the topics fit together. That's all. I think it'll help you retain this stuff to have kind of a good framework of how it all fits together in your head. So this isn't something where I expect to take points off or anything. The only way you'll lose points on this is if you really don't do it, or, you know, Yep. So each of the two problem sets are worth 5% of your grade, that means, because the problem sets together are 10%. So yeah, it's 3 points, but it's 5% of your grade. So I think I've heard of that happening, people saying before, you know, like, oh, these are only worth 3 points. It's not even worth doing this. Well, like my points aren't all equal to the same thing. You have to think about the percentages, you know. So yeah, it is important. Don't skip one of the problem sets. No. So, I mean, I think, so this really, I mean, it's going to take some kind of, a little bit of depth to your understanding of what all these things are, how the different things relate together, and I think that's an important thing to get. So like right now, I don't want to give any hints. If you come in with stuff that you've worked on, I'd be happy to tell you what works, what doesn't, and then, you know, the more you show me you've worked on it, the more I'd be willing to give advice or whatever. But first, I want you to just spend some time thinking about these things and how they relate to each other. I think it's an important thing to do. Question? Yep. Oh yeah, I'm sorry that, oh, post it online. Okay, so for this class, So I probably told you, right, what, I should have told you what, if I didn't tell you what your score was, then you got 3 out of 3. If you didn't get 3 out of 3, I told you what your score was. So, so post it online. I guess I'll try to do that. But it's, you know, it's like things get hectic at the end for us too. So,
Do you want us to solve the problem in the right?
yes, that it says that on the, yes, make up a single problem and solve it. Yep. Yeah. So, you know, like once you start getting into the right ballpark, you know, it's sort of in your interest to try to figure out a way to simplify the calculations as much as you can, you know, because, yeah, you have to solve it. And I don't discourage that. I mean, I think that's great because you know, to make a simple problem that incorporates these things, you know, takes sort of understanding how they fit together. So, so yeah, that's great.
Does it have to be a complex circuit?
Nope.
Or is it a neutral circuit?
Yep.
Okay.
That's right. Any other questions? All right. And then the semester's over. 1 year of your life gone. Okay, so now we're going into the last topic, and that is electromagnetic induction. Boy, you know what you really notice when you bike to work every day? You really notice how many dead animals there are lying around. Like, it's quite a alarming number. And I just see them each day looking a little worse. Smelling a little worse. Well, like on my ride, there is a goose lying there, a raccoon with this expression.
There was a deer on the entryway of 35.
Oh, God. Gross. There is a cardinal. Yeah. And there is a rabbit's leg. Very gross. Just like chewed off, like the body was chewed away and the leg remains. And I see all these things every single day, day after day. I know. And I told you guys about the eagle thing I saw, right? Well, you weren't here. Okay. Okay, so back to electromagnetic induction. So here's kind of here's the lead in. Electricity and magnetism is broken up into two parts. The first one is how electric current produces magnetic fields. And now we're done with this one. And now we're going on to the second one, which is how some, so not all electric currents produce magnetic fields, but not all magnetic fields produce electric currents. But in some cases, magnetic fields produce electric currents. Um,
So all electric currents are using magnetic fields, but not all magnetic.
right. Yep. These electric currents that are created by these magnetic fields are called induced currents, and that's where the electromagnetic induction name comes from. And so this is what we're on now. This is induction. And so the first question is, what does it take for a magnetic field to produce a current? So when does a magnetic field produce or induce, let's say induce here, induce a current? And the answer is when the magnetic flux changes. Okay, so what the hell is a magnetic flux? What the hell is a magnetic flux? Okay, so the first thing we have to talk about is how to calculate the magnetic flux. And then if the magnetic flux is changing, we'll talk about how it creates a current. Magnetic flux, of course, is cool because the word flux is cool, because like flux capacitors and stuff. Because, and also another thing, what 80s movie is that? Back to the Future. You should see that, Kaylee. Okay, good job.
I was hoping you would say mannequin.
No, but that's what I was hoping you were going to say. What? Okay, so Back to the Future. Good job. They use the flux capacitor. That's not a real thing, obviously, but you know, flux. That makes magnetic flux sound really, really high tech. Another thing that's funny about Back to the Future is constantly in the movie, what's the guy's name? Christopher, the scientist, the doctor or whatever, the professor or whatever. He keeps calling the amount of energy they need a gigawatt. And what he really means is a gigawatt, which is funny to us now. Like if you watch it now, it really hits you. Like, is he talking about a gigawatt? And they didn't even get him to pronounce it right. But like, it's a funny thing. Like now giga is a common term for us. But just 30 years ago, giga was like, there wasn't really giga anything in our life, you know? Like computers were like kilobytes were how we measured computer memory, you know? Now it's gigabytes, you know? And terabytes.
Yeah, for the external hard drive.
Yeah, so that's funny. When you watch it, that's funny. Whenever he says gigawatts, he means gigawatt.
Just remember that.
Yeah. Okay, so the magnetic flux. If you have, so let's imagine that you have a coil of wire and this wire is in the presence of a magnetic field, a constant magnetic field. So let's say all of these B vectors are the same. This wire, if you imagine this wire being drawn on a piece of paper, okay? And you stick that piece of paper up on the board or on your paper or whatever. okay, with a pin, okay? You need to imagine this pin would be like perpendicular to the shape, okay? And to calculate the magnetic flux, you have to imagine that perpendicular thing, like that pin, that skewer that's skewering this thing to the paper. So, okay, this is it. It's a normal vector, it's called. You have to imagine this line running both ways through the shape perpendicular to it. Are you imagining that?
Yep.
Are you really?
Wait, that's the pin.
That's the pin that, so like if you drew this shape on a piece of paper, so it's a circle. Like right now I have it drawn like 3D, but imagine it's a circle. And you took a pin and stuck it up on the board, okay? Then the orientation of that shape, for our purposes, is not represented by the circle. The orientation is represented by the pin, okay? It's a common thing in math, but it's a little odd when you first see it. Okay, so this line is perpendicular to the plane that the wire sits in. I'll call it the loop, the wire loop. Okay. And this line, I'll just call the normal, let's call it the normal line. Okay. Then to calculate the magnetic flux, we're going to write it as a capital Greek letter phi with a subscript b. The subscript b says this is the magnetic flux due to the magnetic field B. And it is equal to the strength of the magnetic field times the area of the loop. I'll write all this stuff again. Times the cosine of some angle theta. So this is the equation. B is the magnitude of the B vector. A is the area of the wire loop. And theta, now this is where you have to imagine that perpendicular line, that normal line. Theta is the angle between the B vector and the normal line. Okay, so theta in this drawing would be this angle here. Anyone have any questions about the normal line, calculating that angle? Calculating that angle is the most confusing thing about the flux. What? This is the loop. So if you calculated the area of this circle, that's A. Yep.
How are we supposed to find the angle?
It'll be given. Yeah. So what angle maximizes the magnetic flux? 90 degrees. And what angle makes the magnetic flux 0? 0 degrees. Okay, so if this magnetic field vector B was oriented straight up, then this would be maximized. Wait, I told you the wrong things. I told you everything exactly backwards, sorry. Cosine is is 1 when theta is 0. And cosine is 0 when theta is 90. Okay? So this angle is 0, would be 0 in this drawing if these b vectors were going straight up to the top of the screen, right? Then it would be parallel with that normal line. You'd have a 0-degree angle, and so you'd have cosine of 0, which would be 1. That would be the biggest the magnetic flux could be for this given size of the loop and this strength of a magnetic field. And it would be 0, there'd be no magnetic flux if those b vectors were lying flat in the plane of that wire is in. So if they were like pointed straight to the right, okay, or to the left, then the angle would be 90. Cosine of 90 is 0, and you'd have no magnetic flux. Okay, any questions about that?
Is the normal line always perpendicular to the loop?
Yes. Yeah, normal means perpendicular, so that's the definition of it. Yep. And so what this is calculating in a way, if you think of flux as something leaving, a flux is a measurement of how much of this, so if you think of the loop as kind of like a window, the magnetic flux in a way is a measurement of how much magnetic field is going through that window, is leaving through that window, okay? If all of these are lying flat down on the wire, then nothing's going through the window. They're going parallel to it. If everything's perpendicular to this, then all of those magnetic field vectors are pointed out and leaving, okay? So that's where the name flux comes from.
Can you show how it's flat in the drawing? Like, it just like, it becomes 0, right? Like drawing.
Yes.
When you say flat, you don't mean perpendicular to the normal line, or do you?
Okay. So let's think of the loop. Here's an example. Think of a circular loop like that, okay? If the magnetic field vectors are this way, and these have to be everywhere in here, it has to be constant, so I'm just drawing a few, but okay. Or if they're all going into the page, what does the normal line look like? It's going out of and into the board, right? So in these two pictures, what is the angle between the magnetic field vectors that I drew and the normal line? 0. They're parallel to each other. Yep, so in this case, theta is equal to 0, so cosine of theta is equal to 1, okay? Now, with same wire, what if the vectors were this way, or this way, or, you can imagine infinitely many orientations as these just turn in different directions. But the key thing is they're in the same plane that wire is in. okay? In that case, theta is equal to 90 degrees because the skewer that you would use to pin this up is like this, right? The angle between this and this is 90. So theta is 90, cosine of theta is 0. Yep.
You'll give us the angle unless it's 90 or 0.
Unless it's 90 or 0, yep. And pretty much all the problems, it's going to be either 90 or 0. But figuring out which one it is important. You know, you'll get your answers backwards if you get this idea wrong. Any other questions about that? Okay, so that's the magnetic flux. So changes in the magnetic flux produce an electromotive force we're just always going to call it an EMF in the wire. You can just think of the EMF as a voltage. If you also know the resistance of the wire, you can use Ohm's law to calculate the induced current. Okay, so Ohm's law says V equals IR. Our voltage is going to be, this fancy E is the EMF. So the EMF is equal to the induced current times the resistance. I is the induced current. Okay, so to calculate the EMF, to calculate the EMF, if you have a single loop of wire, then you use this formula that says the magnitude of the EMF is equal to the equation's always written like this. And so this is how I'm going to give it to you. But the way to really think about it is forget about this negative sign. That negative sign is only when you're doing the full vector form. And treat this as an absolute value. All we're doing is getting a magnitude of the EMF. Okay? For a coil of wire, with N loops, you'll use the formula that says EMF is equal to negative N times the change in the magnetic flux over the change in time. And again, this is just how you always see it written, so that's how I'm going to give it to you. But cancel the negative and remember that we're talking about absolute value. Okay. So when you're doing a problem like this, trying to figure out the induced current, you're going to first figure out that angle, calculate the EMF at two different instants, okay? Use this formula to figure out what the EMF is from that difference in magnetic flux, and then use Ohm's law to calculate the induced current. Okay, so there's one thing missing so far. So we've calculated the magnitude of the current, but current has a magnitude and a direction. So we need a way to figure out the direction of the induced current, okay? So to get the magnitude of the induced current I, you're going to first calculate the magnetic flux at two instants. Then you're going to use that to calculate the EMF. Then you're going to use the EMF is equal to IR to calculate the induced current. For the direction of the induced current, we're going to use something called Lenz's law. Lenz was a person. And I think the easiest way to think about Lenz's law is this. Before the current is induced, there's a magnetic field B1. The induced current, you know, all currents produce magnetic fields, so this induced current has its own magnetic field, and this is where things get sort of confusing to think about. The induced current has its own magnetic field that we'll call B2. If the magnetic flux is increasing, I guess I'll just write this as the symbol. So if this magnetic flux is, well, let me say decreasing first. If it's decreasing, B2 and B1 are in the same direction. If, on the other hand, the magnetic flux is increasing, then B2 and B1 are in opposite directions. Once you've figured out the direction of the magnetic field produced by the induced current, the induced current must agree with B2 according to right-hand rule number 2 from the last topic. Okay, so this is just a lot of stuff that you have to remember. So basically, once you've calculated the magnitude of the induced current, you have to figure out whether, look at your two flux values at your two instants. Did it increase or did it decrease over that time interval? If it decreased, then your induced current's magnetic field is in the same direction as your original magnetic field. If the magnetic flux increased, then your new magnetic field is in the opposite direction of your original magnetic field. Once you figure that out, then your thumb represents the magnetic field vector. So I guess let me so your thumb represents that magnetic field B2, and your fingers represent the induced current. Okay. Any questions about that? I mean, I think there's no way it could be totally clear right now, but anything strike you as being confusing yet? We'll just go through a bunch of problems, and I think that'll help clear up a lot of this. Okay.
So what's that sign again, the I with the 0 in it?
Oh, that is phi. Like, this is lowercase phi, and this is uppercase phi. Yeah.
So what does it signify again?
The flux, the magnetic flux. Kaylee, you have a question? Okay.
All right, so if we're doing a right-hand rule, say this is our loop,
Mm-hmm.
and it's going this way, the magnetic field
Right.
vectors, wouldn't they always be parallel with the normal line then?
Yes.
Okay, so then how are...
That's a good question. Yeah, that's a really good question. So the answer is they are as close to the same direction or opposite direction as you can be with the angle that you have. Most of the problems we're doing are going to be 0 and 90 degrees.
Yeah.
But yeah, in this funny case, yeah, that's a really good question. So say that the magnetic flux was decreasing in this example. Yeah, so if it's decreasing, then B2 is this way, supposedly, right? So really, according to the right-hand rule, it has to be perpendicular. So the question is it this or this? It's the one that's closest to this, which is like that. Okay. We're not, I don't...
equation going like skewed off.
Because this isn't B2, this is B1.
Oh, okay.
Yeah. That's the original magnetic field, and we're going to calculate the magnetic field that's produced. For which one? Yeah.
What is the loop present in number?
The number of loops of wire. So if you have a big coil of wire, you get a bigger EMF than if you have a single wire. Yep.
So you cross out the negative, is that all the time?
All the time.
That's never gonna
Yeah.
come back
No,
for this.
that equation, I'm going to write it without the absolute values and with the negative, because for some reason that's how people write it. I mean, I know why they write it that way, because if you do the full vector form of these equations, that tells you the direction. But since we're not using this for direction, that negative is nothing to us. So just cross that out and remember that we're talking about absolute values. All right. So here's the first example. So let's say that there is a magnetic field of 0.01 Tesla into the page. And we have a loop of wire that goes from a circle with a radius of 0.1 meters. So I'll just give you the area. If that's 0.1 meters, then the area would be 0.03142 meters squared. And the magnetic field vectors are going like this. And then a little bit of time elapses, and as this wire is squished together, and we get, the loop looks like this. Okay, you're just squishing that wire. So there's those magnetic field vectors. And let's say that in this one, in this configuration at instant 2, the area is 0.003042 meters squared. And let's say that the time that elapses is 0.05 seconds. And let's say the resistance of the wire is 0.5 ohms. Okay. What's the induced current? So the magnetic field that's drawn there, this is the magnetic field 0.01 Tesla. Is that B1 or B2? That's B1, yep. So the one that's given in the problem is B1. Well, actually you can have problems where that's not given either, where you have to calculate that from a current. And then this, because this can get so confusing, you know, because you can have an original current that's producing your magnetic field B1 that then causes a current that then causes a magnetic field. So basically, you can end up with a current I1 and its magnetic field B1 causing a current I2 and its magnetic field B2. And so there's a lot of bookkeeping that you have to do here.
You're not gonna do that to somebody.
Well, I'm not going to, I could keep it going forever. I'm not going to do that. But yeah, there'll be times when you have two currents and two magnetic fields and you have to keep straight which one is which.
infinite number of times?
Yeah, that's what an electromagnetic wave is. So like light or heat radiation.
Sorry.
No, that's fine. I just was trying to figure out what that is. I thought it was another animal dying. So heat radiation or light or radio waves, all that stuff is this infinite sequence of currents producing magnetic fields, producing currents, producing magnetic fields.
And no energy is lost in that?
No energy. Definitely not very much energy is lost, but I suppose, well, very little energy is lost. The farther away you go, the farther away you are from the source, the less of that signal you get. But that's not because of energy being lost. That's because of, remember that thing with sound waves in 3D? That the farther away you are, the smaller chunk of that original energy gets to you. And so the farther you are, you know, like it's hard for us to get radio signals from Russia or something. But that's mostly just because we're getting such a small fraction of that original energy. So yeah, I think it's fair to say a very tiny fraction is lost actually. Okay, so what's the induced current? So let's first calculate the magnitude of the induced current, and then we'll calculate the direction. So at instant 1, to calculate the flux, what's the magnitude of the magnetic field? .01. What's the area of the wire? It's given, yeah, 0.03142. And what is the angle between that normal line and the magnetic field B1?
0.
That's right. So you have cosine of 0. And so that all goes away, and you just have 0.003142. And the units are Tesla meters squared. And now at instant 2, the magnetic flux, what's the magnetic field here? Well, in this problem, that doesn't change, so that's still 0.01 Tesla. The area at instant 2 is this new area because it's squished down, so 0.003042. And what's the angle between the normal line of this shape and the magnetic field?
0.
It's still 0. Yep, we haven't changed the orientation of that wire. We've just squished it. So cosine of 0 degrees. And so you get a value of 0.000342. This is a single loop of wire. It's not a coil of wire. So the EMF is going to be the absolute value of 0.003142 minus 0.0003042 divided by the elapsed time. And it was given that the elapsed time was 0.05 seconds. And you get a value of 0.0057. And what are the units of EMF? Well, what are we thinking of? How are we treating EMF? Like, basically what is it? Yeah, it's basically voltage, so it's going to have units of volts. All right, so there's the EMF. The last thing we have to do is calculate the induced current. Ohm's law says 0.0057 is equal to the resistance, that's 0.5, times the induced current. And so I is equal to I is equal to 0.0114 amps. Okay, so that's the magnitude of the current. Now we have to use Lenz's law for the direction. In the problem definition, the magnetic field vector B1 is into the page. Okay. Is the magnetic flux increasing or decreasing? The magnetic flux is decreasing. You can just look at the two values. And so what direction is B2? Yep, it's decreasing, so it's in the same direction. So B2 is like that. And if B2 is into the page, what's the direction of the current? Well, so think of it as a current going around the coil. Your thumb's into the page, and so the current direction is this way. So you end up with a clockwise current of 0.011 amps, 114 amps. Yep. Because when you look at those two instants, you calculate the magnetic flux at instant 1, calculated at instant 2. It's bigger here than here. Any questions right now about that problem? Okay, so I have a question for you to think about. Okay, so, and why am I asking this question? So, magnetic flux is not a super intuitive thing. It's not like it's not a physical thing that you measure with one measurement, you know. It involves a bunch of physical measurements, right? The magnetic field strength is a measurement, the area is a measurement, that angle is a measurement. So I want you to think for a second about physically what you would do to the wire or the magnetic field or both. What are the changes you could make to cause an EMF, to induce a current? You know that something has to change, that magnetic flux has to change. What are the ways you could physically change the wire and or the magnetic field to induce a current? Okay, so, I mean, like, what if you wrapped a pink bow around the wire? You know, would that induce a current? Or what if you dump dirt on it? Neither of those probably would. But like, what things could you do to the wire or the magnetic field? Bend it. Yes, so that's one. And so you could change the shape of the wire. Yeah, but we're usually thinking of this in terms of pretty high frequency changes. So, so yeah, you're right, that would do it, but that's not one of the ones I'm thinking of.
The angulation.
Yes, that's right. You could change the orientation of the wire or of the magnetic field.
If you change the wire, won't it change the magnetic field?
If you change the wire, it'll change the magnetic field B2, but it won't change the magnetic field B1. That B1 magnetic field that you're starting the problem with isn't affected by what you do to the wire. Only its magnetic field is. Any other
So like say the B1 is like from another electric field
Right.
that is acting on it. Can
Right.
you move that electric field like farther, closer away?
Yep, and that's the third one. And I'm going to just write that as you can change the strength of the magnetic field. Yep. Okay, and so those are the three ways. And how can you remember what those three things are? Well, they all just come from the definition of the magnetic flux. Okay, so changing the shape of the wire changes A. Changing the orientation changes theta. Changing the strength changes B. Those are the only three things multiplied together, so those are the only three things that you can do to change the magnetic flux. Okay, and different ones of these are used in different applications. So the next example I'm going to do, let's wait until Monday. Not Monday, because you don't come here on Monday. But I'm going to do an example where instead of changing the shape, we change the orientation of the wire. And that's sort of a cool one, actually, an important one, because that's how electric generators are made. You have a magnetic field. You use some external source of energy to spin a wire around fast in that magnetic field. That changes the flux, and that changing flux induces a current in the wire. Then you store up that electrical energy that's induced, and that's how you generate electricity. Any other questions? Okay, have a good weekend.